Alright, so now that we've talked about how to compute logarithms, we're going to talk about graphing logarithmic functions. Similar to an exponential function, a logarithmic function with a base of a has a base defined to be bigger than 0 and not equal to 1. And then we're going to get the function that takes the form f of x equals log base a of x. Unlike exponential functions, this particular function has a domain of 0 to infinity, not including 0. We draw a distinction here because exponential functions have a domain of all real numbers, but recall that logarithmic expressions can only take on positive values. They can't take on 0 or negative values. Before we actually start plotting graphs, I want to give you an idea of what a logarithmic function looks like, and we're going to compare this to exponential functions. We already know that exponential functions have the following curve shapes, and we know that they go up or go down, or they have varying steepness levels depending on the actual base. Logarithmic functions actually look a little bit similar, but instead of being drawn above the x-axis like exponential functions are, they are drawn to the right of the y-axis. So as we move forward and start graphing logarithmic functions, I want you to think about pictures that look like the graphs on the right here. They stay to the right of the y-axis, and they follow these basic curves that, again, are pretty similar to exponential functions. Let's jump right in and look at the graph of log base 2 of x. And we're going to do what we did last time, which is plot an xy chart so we have an idea of where these points are lying on the xy plane. But what are we going to start putting into these values? Because we have to think a little bit about how to compute logs. The most straightforward approach is to plug in known powers of 2. Because computing logs means finding the exponent that got us to particular values. So if I plug in powers of 2 for the x values, I already know what the log is going to return. So I'm going to plug in the values 2 to the minus 1, 1, which is technically 2 to the 0, and then 2, which is technically 2 to the 1. This means that as output, I'll get values from the log function of -1, 0, and 1, respectively. So at the end of the day, I have plugged in for my x values 2 to the minus 1, 2 to the 0, and 2 to the first. The log function returned the corresponding exponents in each case, -1, 0, and 1. That's why I'm plugging in these values, because now the logs are easy to compute. I already know the exponent that it's going to return. So now that we're here, let's plot the points and sketch the curve that follows along those points. We'll notice immediately that log base 2 of x goes to minus infinity as x approaches 0. In other words, as my function gets close to the y-axis, my function is going down very fast and approaching negative infinity. And unlike the exponential function, the logarithmic function here has an x-intercept. It looks like it's crossing the x-axis at the coordinate 1, 0. Again, I know that when I take 2 to the 0 power, I get 1 as a result. So when I put 1 into the log base 2 function, the question becomes, what power do I raise a 2 to get the number 1? And that power becomes a 0. For our next function, we'll look at f of x equals to log base 1/3 of x. And again, I'm going to plug in powers of 1/3. The general strategy is whatever my base is, I'm going to plug in for x that base value to the -1, to the 0, and to the first power. So when I take 1/3 to the first power, I get 1/3. When I take 1/3 to the 0 power, I get 0. And when I take 1/3 to the negative first power, I get 3. And these are my corresponding log outputs. Now I just have to sketch the points and sketch the curve, and I get now this decreasing log function. It still crosses the x-axis at the same location of the previous graph, but now the graph goes to positive infinity as x approaches the y-axis, and the log function goes to negative infinity as x goes to positive infinity. Similar to what we did for exponential functions, let's categorize some of the properties that we get. So consider the logarithmic function f of x equals log base a of x. In the case that a is bigger than 1, then the graph is going to resemble the following. I'm going to get this increasing curve that has a vertical asymptote at x equals 0 and increases for all values from 0 to infinity. On the other hand, if the base a is between 0 and 1, then the graph resembles this decreasing curve. It'll still have a vertical asymptote of x equals 0, but now decreases for all real numbers from 0 to infinity. The common trait for these functions is that they both have a domain of 0 to infinity, not including 0, and a range from minus infinity to positive infinity. An important thing to remember as well is that values like log base a of 0 and log base a of -1 are undefined because I can't put in values for 0 and -1 and actually get an answer. I'm not going to have any real valued solutions to these two things. But this really just corresponds to the statement that the logarithmic function has a domain of 0 to infinity. The graphing strategy goes as follows, and this really summarizes what I was saying in the last slide. Whenever I have a logarithmic function whose base a is bigger than 1, I'm going to plug in the values for x, 1 over a, 0, and a, because those will output -1, 0, and 1 respectively. And likewise, if my base is between 0 and 1, I'll plug in the values a, 1, and 1 over a, because then those will give me the output values of 1, 0, and -1 respectively. So it's the same values in both cases, but the order is different. Because when I'm looking at the size of a, that does affect the order when I'm looking at the quotient of 1 over a or just a itself. Really quickly, since we're talking about the log function, we need to bring up Euler's constant. Now, Euler's constant, usually denoted by lowercase e, which is about 2.71 ... It's one of those repeating decimal numbers like pi. It's a number that shows up in nature and never ends. And when you're studying applied or pure mathematics, pretty much in any context, this number shows up all over the place. So it gets a special name and special recognition. In Calculus 1, you'll talk about where this number comes from. But since it's known as Euler's constant, and yes, it is pronounced Euler, not Euler, it's because this is a French name, this actually gets its own special log function. So whenever we need to use log base e of x, we simply just denote this with the letters ln. This means the natural log function. And really it's just a logarithmic function with a particular base, namely this long decimal number. And most calculators even have an ln button. Even your iPhone calculator has this. So let's graph another log function. Let f of x equal to 2 minus log base 4 of x. And I'm going to rearrange this algebraically just a little to write it as negative log base 4 of x plus 2. And here's the reason I'm doing that. Think back to the exponential functions video where these negative signs and these additions and subtractions were able to kind of transform or manipulate our graphs a little bit. And that's really what's going to happen here. Now that negative in front of the log is going to amount to a flip of the graph, because log base 4 of x by itself, having a base bigger than 1, would be one of those increasing curves that we saw. But that negative is going to turn it upside down, and we'll see that once we start plotting these values. What I'm going to do first is look at just the log part of this function, namely the log base 4 of x by itself, not all of f of x yet. I want to be comfortable with the computational part first. When I plug in 1/4, 1, and 4, according to our graphing strategy, I'm going to get -1, 0, and 1. So I already know what the log is going to output in all these cases. Now I'm going to look at the xy chart for f of x itself. Using the outputs we got for just the log part, I'll see that I'm going to get function outputs of 3, 2, and 1 respectively. So why was this easier? All I was trying to do was think about the log part only on its own. And now that I know those outputs, I can feed that through the rest of the function. So to get the function output of 1/4, I just take that -1, I multiply it by a -1, and then I add a 2, that gets me a 3. Likewise, I take that output of 0, multiply it by a negative, add a 2, and I get a 2. And then finally, I take that output of 1, multiply it by minus, add a 2, and then I get a 1. Now, if you weren't crazy about how I broke this down, that's fine. You can always just plug these values into the original function and sidestep what I was doing here. This was just my way of trying to compartmentalize it and turn it into a smaller problem. But now that I have these values and I'm using the second xy chart, I can plot my points and sketch the curve. So if the function that we had was just log base 4 of x by itself, I should have an increasing curve, right? And I would, normally, but that -1 right in front of my log function flips it upside down. So that's why it looks like this. And this function does eventually cross the x-axis, it just takes quite a bit for that to actually happen. So we're not going to see it on the actual window we have carved out here. So we'll conclude this video with a brief introduction to logarithmic equations. Suppose that we want to solve log base 6 of 2x equals to -1. When we were solving basic exponential equations, we had to use this process of making the bases match. But here, this is going to be a little bit more straightforward. Right now, our equation is written in what we would call logarithmic form because I see a log term in my equation. But what I'm going to do is use our relation between logarithms and exponentials to convert this into exponential form. This is going to give me the equivalent statement 6 to the -1 equals to 2x. If you need to review the previous video or the corresponding notes for the relationship, that's totally fine. I encourage you to do that. But the relation says that when I have log base a of y equals to x, I can turn that into ax equals to y. And that's all I've done here. The reason I've done that is that it takes my x, the variable I'm trying to solve for, out of the logarithm and on its own side of the equation. This ultimately just turns it into a linear equation that's easier to solve. In this case, 6 to the minus 1 equals to 2x turns into 1 divided by 6 equals to 2x, and that's just going to give me a solution of x equals to 1/12. So solving a basic logarithmic equation really just comes down to turning a logarithmic form equation into an exponential form equation and solving for x. Let's look at a couple of examples. Suppose that I have 2 times log base 16 of x minus 3 over 2 is equal to 0. So first and foremost, this is not in logarithmic form. I know that because at the top of the slide, logarithmic form seems to have one log term on the left-hand side of the equation and all my numbers are on the other side of the equation. But that's not happening here. I have a 2 being multiplied by my log expression, and I have a minus 3/2 on the left-hand side. So to fix this, I'm going to solve for log base 16 of x. In other words, I'm going to isolate the log term by itself and push all numbers on the other side. By doing so, I'm going to add a 3/2 to both sides, and then I'm going to divide both sides by 2. This will give me the expression log base 16 of x equals to 3 divided by 4. This is now in logarithmic form, so I can change it into exponential form, which will be 16 to the 3 over 4 equals to x. Now solving for x, at this point, is pretty much already solved for. I can just simplify it using our properties of exponents. Once I go through these operations, I'll find a final answer of x equals to 8, and we're done. For our next example, consider log base 5 of 5 raised to the log base 4 of x equals to 2. Now before you start to feel sad just by the sight of this, I promise you it resolves in a pretty nice way. First and foremost, we have to remember that we have canceling rules for logarithms. Right now I have a log with a base of 5, and inside an exponential with a base of 5. Automatically, I get that log and that base of 5 on both cases are going to cancel out. This is just going to give me the expression log base 4 of x equals to 2. Now that I've observed that cancellation, I can rewrite this into exponential form, which will be 4 squared equals to x. And the hard part's over. We just get a final answer of x equals to 16, and we're done. For our last example, look at the natural log of the 5th root of e equals to 2x. Go ahead and rewrite that 5th root of e as e raised to the 1/5, and then apply the exact same cancellation law that we did in the previous example, because remember the natural log function is the log with the base of e. So those canceling terms give me 1/5 is equal to 2x, and that gives me a final answer of x equals to 1 divided by 10. In section 6.5, we're going to talk more about logarithmic and exponential equations and how they can work together to really help us solve for x, especially in strategies where this changing from logarithmic to exponential form strategy doesn't work, or where matching the basis for an exponential equation doesn't work. Join us at 6.5, and then we'll also see in section 6.4 on properties of logarithms.